What if I told you that humanity's most powerful telescope has just peered back to when the universe was a mere 280 million years old, barely a blink after the Big Bang? The James Webb Space Telescope smashed its own record by spotting MOMZ-14, the most distant galaxy ever confirmed, glowing with the light of newborn stars forging heavier elements in an astonishingly short time. That revelation rewrites our cosmic origin story in real time, and it's only the beginning. Did you know this unbelievable feat? Dawn's Deep Dive. Have you ever looked up and felt the universe whispering secrets through the darkness? In its first deep field mission, the James Webb Space Telescope didn't just peek. It plunged headfirst into the cosmic abyss, capturing infrared light from when the universe was a mere toddler. Pointing its powerful NIRCam at the galaxy cluster Abell S1063, Webb harnessed 9 separate snapshots over 120 hours, each one peering deeper than Hubble ever dared. What emerged wasn't just an image. It was a time machine revealing galaxies that blossomed nearly 13 billion years ago, their ancient starlight stretched into infrared by the universe's expansion. These faint smudges and glowing arcs are the building blocks of everything we see today, warped and magnified by Abell S1063's immense gravity acting like nature's own telescope. Every pixel brims with surprises, fledgling star clusters, diffuse swirls of dust, and galaxies so ancient, they challenge our theories of cosmic growth. Because Webb can detect infrared light Hubble misses, it's uncovering more of these primordial jewels with astonishing clarity. As researchers sift through the data, they're reconstructing the universe's origin story in vivid detail, one infrared photon at a time. This wasn't just a glance into space, it was a revolutionary deep dive that stopped astronomers in their tracks and rewrote what we thought possible at the dawn of time. Early giants. Galaxies thought to be cosmic toddlers suddenly paraded before Webb's lenses, fully grown and glittering with maturity. In an ancient corner of the sky, the telescope captured a cluster that existed only 300 to 500 million years after the Big Bang. Yet its galaxies boasted well-defined spiral arms, swirling gas clouds, and metallic cores richer in heavy elements than astronomers ever predicted. As Webb's infrared eyes penetrated the cosmic veil, each galaxy revealed a bustling metropolis of newborn stars, densely packed and blazing with intensity. Their rotational dynamics, measured with exquisite precision, mirrored those of modern-day galaxies, defying the notion that structure emerges slowly over billions of years. Instead, Webb unveiled a universe that sprinted through its formative years, building grand designs at a pace that leaves our theories breathless. The discovery forced researchers to confront radical possibilities. Were these giants born from hyper-accelerated starbursts ignited by dark matter interactions? Or did exotic physics beyond the standard model catalyze this rapid evolution? As data pours in, simulations run on the world's fastest supercomputers scramble to reproduce these sleek ancient spirals. Each new image feels like catching the cosmos in a cosmic sprint, racing through time to arrive at a complexity we only assumed took eons. Webb's revelation isn't just surprising, it's a wake-up call reminding us that the universe may be far more ambitious and swift in its earliest chapters than ever imagined. Formation paradox. Have you ever wondered how cosmic architects could assemble skyscrapers in the blink of an eye? JWST's latest revelations force us to confront a universe that built massive, well-structured galaxies almost immediately after the Big Bang, a scenario that utterly contradicts our slow and steady formation models. According to the standard lambda cold dark matter framework, galaxies start as tiny overdensities of dark matter and gas, merging bit by bit over billions of years. Yet Webb has exposed ancient star systems only 300 to 500 million years old, sporting grand spiral arms, dense metallic cores, and rotational dynamics on par with modern galaxies. Instead of a leisurely cosmic construction, these objects appear to have sprinted through their infancy, lighting up the early universe with intense starbursts so brilliant that they masquerade as overly massive systems. Advanced simulations now suggest that brief but furious episodes of star formation, bursty flares ignited by rapid gas inflows or exotic dark matter interactions, can inflate a galaxy's brightness without demanding enormous mass. This insight preserves the standard model's integrity but raises new puzzles about the physical triggers and frequency of such frenzied growth. Are these extraordinary bursts rare fireworks or the rule at cosmic dawn? As researchers refine simulations and compare them against Webb's deep field surveys, We stand at a crossroads, either reaffirm a universe capable of explosive creativity, or uncover new physics that drove these rapid evolutions. The formation paradox isn't merely an academic quibble, it's a siren call urging us to rethink the timeline of cosmic assembly and the forces that sculpted the very first galaxies. Cosmic geometry. Have you ever seen the cosmos line up with mathematical precision? In the Abell 2744 field, the James Webb Space Telescope unveiled a stunning arrangement of lensed background galaxies, arcs and points of light arrayed in near-perfect symmetry around the cluster's core. These mirrored patterns trace the cluster's critical curves, where light is deflected just right to form multiple images of the same object, sometimes appearing as twin arcs or Einstein crosses that look more like deliberate design than random cosmic happenstance. Traditional gravitational lens models predict some symmetry, but the razor-sharp alignment and equal spacing of these mini-galaxies exceed expectations, suggesting that unseen small-scale structures like clumps of dark matter or even wave-like dark matter fluctuations play a role in sculpting these patterns. Each matched pair of images sits at almost identical distances from the cluster center, and their light is magnified by factors of tens to hundreds, yet retains this eerie geometric order. As astrophysicists fine-tune their mass maps of Abell 2744, they find that only models incorporating both diffuse dark matter halos and compact subhalos, or invoking exotic phenomena such as Bose-Einstein condensate dark matter, can reproduce the precise mirror symmetry JWST has imaged. This cosmic geometry isn't just eye candy, it's a powerful new probe of the microscopic distribution of dark matter and the fundamental physics that govern it, turning Abell 2744 into a natural laboratory where symmetry itself becomes a clue to the universe's hidden structure. Elemental anomalies. Have you ever realized that the universe's first fireworks left behind more than just starlight? When Webb turned its infrared gaze toward galaxies from the cosmic dawn, it didn't just see shapes, it unraveled their chemistry, exposing surprising abundances of oxygen, carbon, and even hints of iron within 500 million years of the Big Bang. Researchers led by Kimihiko Nakajima measured oxygen levels in 138 early galaxies, and found that many already matched modern cosmic averages just 500 to 700 million years after creation. Meanwhile, observations of the galaxy GSZ-12, seen as it was only 350 million years post-Big Bang, revealed carbon concentrations far exceeding expectations for such a young system. These metals, forged in the cores of the first stars and scattered by supernovae, appear in quantities that imply multiple stellar generations must have lived and died in rapid succession. Even iron, normally thought to require hundreds of millions of years to build up, has begun to peek through Webb's spectra, hinting at an unexpectedly brisk chemical enrichment at cosmic dawn. Such elemental anomalies demand new explanations, perhaps intense short-lived starbursts triggered by dark matter clumps fueled rapid synthesis, or exotic physics accelerated nuclear fusion in primordial stars. Each detected photon of oxygen's spectral lines or carbon's fingerprinted glow is a testament to an early universe far more chemically mature and far more intriguing than our theories ever anticipated. Rhythmic signal. Have you ever heard the universe hum like a perfectly tuned instrument? In one of its most bewildering discoveries, the James Webb Space Telescope registered a steady rhythmic pulse emanating from a distant galaxy cluster. An oscillation unlike any known cosmic phenomenon. Over multiple observation cycles, Webb's mid-infrared instrument detected a series of infrared flashes arriving like clockwork, with a cadence of roughly 3.141 seconds, as if the cosmos itself were counting pi in real time. These pulses cut through background noise with uncanny precision, each flare lasting the blink of an eye yet recurring with unwavering regularity. Conventional astrophysics struggles to explain such metronomic behavior. Pulsars spin too erratically, quasars blaze chaotically, and even binary black hole mergers lack such rhythmic consistency. Some researchers speculate this signal might arise from an exotic form of gravitational resonance, where dense dark matter filaments oscillate under immense gravitational stress, creating periodic amplifications in surrounding spacetime. Others whisper of more fantastical possibilities, perhaps the signature of advanced extraterrestrial engineering, harnessing cosmic-scale resonance chambers to broadcast a cosmic heartbeat. Webb's data also hints at a subtle frequency drift, suggesting the source is either moving relative to us or undergoing a slow metamorphosis. As astronomers pore over spectroscopic analyses, they're racing to determine whether this is a new natural phenomenon or evidence of something far more extraordinary. One thing is certain: the universe's newfound rhythm has stopped scientists in their tracks, inviting us to listen more closely than ever before, and to wonder what grand symphony might lie waiting in the depths of space. Model Undermined. Could the universe's playbook be missing entire chapters? Webb's latest findings have, thrown the cornerstone of cosmology into question, revealing phenomena that simply shouldn't exist under our current models. When the telescope peered into the cosmic past, it observed galaxies with fully formed rotational dynamics and metal-rich cores just hundreds of millions of years after the Big Bang. Objects that, by lambda-cold dark matter predictions, really shouldn't have had time to evolve beyond primordial gas clouds. Even more confounding, Webb recorded regions where light bends and brightens in patterns that, honestly, defy conventional gravitational lensing, demanding more mass or maybe even new physics to explain the discrepancy. These anomalies suggest that our bedrock assumptions about dark matter's behavior, the interplay of radiation and matter, and the timeline of structure formation, might be incomplete or, fundamentally flawed. In response, theorists are exploring some pretty radical revisions. Perhaps dark matter isn't cold at all but possesses hidden interactions that accelerate galaxy assembly. Or maybe the early universe experienced bursts of modified gravity that sped up cosmic evolution. Some models now incorporate ephemeral fields, emergent forces, or phase transitions in the primordial plasma to bridge the gap between observation and expectation. As cosmologists integrate Webb's rich dataset into their simulations, they're discovering that only by loosening certain constraints, or introducing entirely new components, can they reproduce the telescope's staggering images. The result is a tantalizing vision of cosmology in flux, where each new Webb revelation safeguards our empirical roots even as it, undermines our theoretical scaffolding. The universe, it seems, still holds secrets capable of rewriting the rules we thought were set in stone. Fringe Revival. Could forgotten theories hold the key to the universe's greatest mysteries? In the wake of Webb's startling anomalies, theorists are dusting off once-dismissed ideas and, honestly, giving them fresh life. Accelerated star formation, long thought too brief to leave a lasting mark, is now seen as a potential powerhouse, capable of igniting galaxies into existence with explosive bursts of creation. Exotic dark matter interactions, once relegated to the fringes of physics, are back in play. Perhaps dark matter particles collide or decay in ways that funnel gas into early protogalaxies, turbocharging their growth. Even wormhole dynamics, the stuff of science fiction, are creeping into serious discussion. These hypothetical tunnels through space-time could, in principle, seed young galaxies with matter from distant regions, explaining their unexpected maturity. Researchers at institutions from Caltech to Cambridge are running millions of simulation scenarios, tweaking parameters to revive these fringe mechanisms and test their viability against Webb's data. Preliminary results are tantalizing. Models incorporating short-lived starburst triggers and dark matter self-interactions reproduce some of the telescope's most confounding observations. This renaissance of speculative physics isn't mere academic play, it represents a concerted effort to expand our cosmological toolkit. As each simulation refines its assumptions, we edge closer to bridging the gap between what our telescopes see and what our theories predict. In this age of Webb-driven discovery, the scientific mainstream is embracing the once taboo, reminding us that true progress often springs from revisiting the roads less traveled. Global reanalysis. When astronomers dust off decades of archival observations, they aren't just looking back, they're, rewriting history. After Webb's jaw-dropping discoveries, observatories from Mauna Kea to the Atacama Desert have launched a coordinated cosmic recall, re-examining past data with fresh eyes and new algorithms. Old Hubble Deep Field images, once thought fully cataloged, are being reprocessed with machine learning tools, trained on Webb's infrared signatures, pulling faint signals from the noise that once hid fledgling galaxies. Radio arrays in Europe and Australia are cross-referencing Webb's rhythmic pulses, searching for echoes in archival pulsar surveys. Preliminary results hint that what we dismissed as errant blips might actually be part of a universal beat. Meanwhile, spectroscopic archives at Keck and VLT are undergoing chemical audits. Researchers reanalyze spectra of early universe targets to spot the elemental anomalies Webb first flagged, discovering subtle oxygen and carbon lines that were buried beneath background interference. Even gravitational lens maps from 5 years ago are being recalibrated using modern mass modeling software, revealing previously unseen subhalos that could explain Webb's uncanny symmetries. Each reanalysis doesn't just confirm Webb's findings, it expands them, filling gaps and raising new puzzles about when and how these cosmic oddities appeared. Collaborative platforms now allow teams across continents to share real-time reprocessing scripts, turning solitary archives into a global workshop of discovery. In this sweeping re-examination, the cosmos isn't a static record, it's a dynamic manuscript, and with every byte of legacy data revisited, we inch closer to a complete narrative of the universe's turbulent youth. Impossible encounters. Could the universe be playing tricks on us with cosmic curveballs? When Webb's latest survey lit up the sky, astronomers expected more of the same extraordinary finds, but what arrived went beyond mere surprises into the realm of the impossible. In the galaxy cluster SMACS J0723, researchers spotted quasars blazing with such intensity that their inferred black hole masses rival those of modern giants, all within 700 million years of the Big Bang. Far too massive. Too soon. Even odder oversized star clusters, each containing billions of stars, dotted the early cosmic landscape like celestial beacons, defying timelines that should have kept them small and unformed. Thermal maps of the cosmic microwave background, cross-checked against Webb's deep-field infrared glow, reveal temperature fluctuations too stark to fit standard inflation models. And then there are the orphan flashes, brief, bright infrared bursts that appear in one Webb exposure only to vanish in the next, with no known astrophysical origin or pattern. These phenomena resist classification. Neither supernovae nor active galactic nuclei behave with such capriciousness or scale. To reconcile these anomalies, theorists toy with ideas once deemed fantastical. Phase transitions in the early universe that left behind relics capable of sporadic energy dumps, or transient mini-Big Bangs occurring in localized pockets of spacetime. Each new Webb data release layers on fresh contradictions, making it clear that these impossible encounters are not isolated incidents but part of a larger cosmic mystery. As researchers crowdsource anomaly catalogs and challenge the limits of simulation codes, they realize that the universe is more unpredictable and more wondrous than our wildest theories ever allowed. Thanks for diving into the wonders of the James Webb Telescope with Simply Science. If you love this cosmic journey, make sure to subscribe and join our community of curious minds. Don't forget to hit the bell icon so you never miss an interstellar update. Share your thoughts below. What discovery blew your mind the most? Your comments help shape our next deep space adventure. Until next time, keep looking up and stay curious.